Hello, everybody. I'm going to try to give you an introduction to the distributed software event device. That's a very long name, so I just call it the distributed scheduler. Here's the agenda. I'm going to start to talk about, start to give you an overview. What is this distributed scheduler, a rationale, why we need this new event device. I'm going to try to cover a bit of the implementation aspect of this new event device. I'm going to talk about scheduling, flow migration. I'm going to speculate a bit about what kind of workloads we see that this scheduler can handle. I'm going to talk about what counters we have, what observability we have in the scheduler, and give you some numbers, performance benchmarks, and some pointers for further reading. So I mentioned it already, this is a new DPDK event device. It's a pure software implementation. It's parallel, so scheduling work is distributed among all the participating L cores. So all the L cores that have an event dev port, or using an event dev ports. It supports 3 different queue types: atomic, parallel, and single link. So it does not support ordered. Also, it doesn't support what I call mixed mode, what's in the API called CFG all types, which is a queue where you configure a queue to accept events of all the different scheduling types. And on the right side, you have like a graphical depiction of how the scheduling overhead or scheduling work are distributed among the cores. This is a 4-core systems, and the gray is the scheduling overhead. So with the SV scheduler, what I will call the centralized scheduler, also known as the SQM, you're using a single core, all the cycles on that core basically, and then in the distributed scheduler you have a little bit of scheduling overhead of all the participating L cores. So why we need another software scheduler? Well, and I'm going to use the centralized software scheduler as a reference throughout. So I wanted to avoid using a dedicated scheduler core. And that's both because I wanted to allow scaling down to fewer L cores. Like if you have a system with only 2 L cores, you don't want to use one of those cores for scheduling alone. I also want to allow scaling up to more L cores and/or longer pipelines, so more events per second, more throughput. And this scheduler is able to provide this. Secondary, and this is really secondary, it would be nice if we reduce the scheduling overhead in the process, so as in clock cycles per event. But all these good features, of course, they come at a cost. And the cost primarily is what I call, for the lack of a better word, agility in load balancing. So and the distributed scheduler is much slower to load balance than the centralized scheduler. And this is really a complement to the existing software scheduler in the DPDK. So how does scheduling work in the distributed scheduler? Well, scheduling happens at the time of enqueue. And it's using DPDK event rings for transporting the events, just like the centralized scheduler. And the procedure, the actual logic in queue at the time of enqueue is really simple. You take the event flow ID and hash it to a 15-bit hash, and you use this hash to look up a destination port in a per queue table, what I call flow hash to owning port table here. And then you can just send the event right away. Although for efficiency reasons, the scheduler doesn't do this, at least not always. So to improve efficiency, events are buffered for ring efficiency reasons. I'm going to cover port load estimation. So we keep track of an estimate of how loaded a particular event dev port is. And this is for load balancing reasons. And the procedure is that if a dequeue happens and there are no events, to process, then that port is considered unloaded or idle. And then if it's more than 0, the port is now busy. And then we keep a track of the point of transition. So we take a timestamp at the points of transition between these two states. And periodically, we calculate how much, basically in percent, how much the port is loaded. And the measurement period is currently 250 microseconds. So we get an approximation of the past load, and we use that to estimate future load. So on to flow migration. The purpose of flow migration is to balance load across the event ports. And basically, in detail, that means maintaining a flow hash to owning port table such that no port is overloaded. We don't care so much in case of the ports not being so loaded. We don't care so much about having an evenly distributed load. But we care about when certain ports reach a certain threshold. And the port itself checks every millisecond, is this threshold reached? Am I at a very high load? And if the answer is yes, the port will try to move one of the flows it owns to another port. So first of all, it will query the other port's load estimates to see if there's a suitable candidate. Maybe everyone's loaded, highly loaded, and then there's nothing you can do. And to know, but if there are suitable candidate ports, it will continue to look at the list of last seen events. So to keep track of what flows are actually active, because it could be, it's actually 32K possible flows. So we maintain a list of the last seen events, which is just a short sample of what's last been dequeued on that port. And then from that, we decide which of those flows we'll try to move. And I'm not going to cover the flow migration strategy that's being used in detail. But what I can say is that the smallest of the last seen flows is the first choice for migration. So we try to not move large flows, not create ripples in the system. And this is more the detail of the migration procedure, which is kind of like the most complicated part in the scheduler. The rest of the things are fairly straightforward. And wouldn't it be for atomic and its in-order processing semantics, it would be very simple. It would just be atomically write to a table, and then you're done with it. But now we need to maintain in-order processing. And in order to do this, we're using a under-the-hood singling schema. And that's messaging over DPDK rings. So in addition to the data carrying rings, the event rings in the ports, we also have what I call a control ring, which is a regular DPDK ring, which control messages are sent between the ports. This is all hidden to the application. And it's also asynchronous. So if you initiate a request on the control ring, you don't blockingly wait for a response. You just keep going, just keep track, and then periodically you would pull your control queues to see if there's new messages, so you can change state. One additional requirement, so the scheduler as a whole adheres to the event APIs, but there are, with some slight changes, and that's not new API calls, but you have to behave slightly differently. And the schema requires that there are no unattended ports. So you can't just create a port and leave it there. You have to do enqueue and dequeue operations, because otherwise you won't check your control rings. And if you don't do that, migration will just come to a halt. And what the initiating port will do, initiating as in the port that's trying to move a flow away from him, is to order the other ports to pause the flow. And if the flow is paused, and an event arrives pertaining to that flow on another port, it would just be buffered and sent later. And so an effect of this, when we pause the flow on all the ports, is that the migrated flow would experience a small hiccup. So that would be a latency jitter. And the migrated latency decides the size of the length of the hiccup. And that, in turn, is much dependent on the enqueue or dequeue call rate done by the L-core threads on the ports, which in turn probably is limited by stake processing latency, as in how much application work you do per event, and also the DQ burst size, how large a burst you'll grab. And also for idle ports, if you have such ports, you will still need to do NQ or DQ. And if you don't have anything to NQ and DQ, you do a dummy NQ with 0 events, which is a bit of a hack. I'm readily admitting that. But that's how it currently works. And the rate you do these calls will also put an upper or lower limit on the migration latency. And of course, you could be preempted by the operating system, or if you virtualize all these things can happen, you can be preempted. So I've tried the real-world experience from the scheduler behavior is very limited, but I have done a fair amount of testing in the testbed I have. It's synthetic, but still, that's what I've done. So I think that if you have many small flows, if you have like thousands or tens of thousands of flows, they will just hash out nicely, and there won't be the scheduler will be the load balancing procedure will be capable of redistributing the load in time. The challenge is the larger flows. And if you have a few large flows where the flow event rate change is relatively slow, then you should be OK. So what's flow event rate change? Well, that's the assumption is if you have a flow that has like 1,000 events per second for a period of time, then you expect that flow to keep on going. Maybe not at that exact rate, but still, it will maintain a similar rate. And if it changed abruptly, if it goes from 1,000K to 1 million in a millisecond time, that would be very hard to cope with for the distributed scheduler. But if it's slower, like if it's what I would be imagined, like TCP slow start, should be fairly slow. Even though it's exponential in nature, then we should be able to cope with that. And if you have very bursty flows, say you set up a traffic generator and you send 10 of these flow IDs for a couple of milliseconds at line rate, and then you switch over to 10 other flow IDs and send that line rate, then definitely the distributed scheduler will not be able to cope, rebalance that load in time. And what's a key metric when you think about if you can use this, if this scheduler is able to handle your workload, is the migration rate. And currently, it's set to be 1K hertz per port, so 1,000 migrations per port per second. And you can tweak that. It's kind of dangerous to tweak because you can get the system into oscillation. But so you can make it. Maybe you can make it 10 times faster, but that's, I think, about it. So there's a whole bunch of counters. I'm not going to go through them all in detail. I can say that there's a bunch of counters related to NQ operations and what type they are and what queue they are NQ to, and the same for DQ. We keep track of the number of migrations, and then that's migration from this port, and the average migration latency. So you can see if you have some disturbance in the system slowing down the migrations. We also, as a side effect of the load estimate, we get like an estimate of average processing latency for the application work done on the event as well. We have some counters related to the credit system. The credit system is to handle, basically to provide back pressure, not to overload the scheduler, it works similar as in the centralized scheduler, so I'm not going to cover it in detail. Then we have one which I find very interesting parameter is the load. We also present the load balance. The load estimate. So in DPDK, typically, if you look at it from an OS perspective, all the L-core threads will be 100% loaded, and it's not always so easy to see what the average, how much is idle, just polling an empty ring, and how much is actually doing application work. But with the scheduler, it will present you, it will give you a pretty good, from my experience, pretty good estimate of how much application work, or to what extent that L-core is busy. And this is assuming there's one event type port per L-core, which is often, but not always the case. So I'm going to present to you some throughput numbers, and this is done with a test application, which is a simulated pipeline. It has no real I/O, there's no real M-buffs, there's no real Ethernet devices. Input is always available, so it's kind of like an overload scenario. There's very few migrations because we recycle the events. There's the same flow IDs. So it's a very nice, you could be very friendly to both of these schedulers, and particularly the distributed scheduler. There's only it's only one stage pipeline, and the application in this case doesn't do anything, because this is a pure scheduler throughput benchmark. And it's run on a 14-core Broadway Xeon. As you can see, and the centralized scheduler is run in dedicated mode, except for the one-core case, of course. Then we call RT event scheduler manually from the application. And as you expect, if you start with the centralized scheduler, it will not scale. I mean, it's a serial application, so it will benefit from multiple cores. It will slow down a bit as it gets more peers. And then the distributed scheduler scales linear, pretty much, I think, with the number of cores you add to it. So we're not hitting any memory bottlenecks or anything like that. Yeah. So I also have an efficiency estimate, and this is the scheduling overhead, the clock cycles per event. It's the same test application, but now we've configured a more real-world pipeline. It's a 5-stage pipeline with 1,000 clock cycles of work per stage. And this work has almost 0 working sets, so all the caches are left to the schedulers, basically. So it's also a scheduler-friendly benchmark. The estimates for the centralized scheduler, the blue line, is it takes the core cycle spent on the dedicated core into account. So the 461 is including the scheduler, the cores, the cycle spent on the dedicated cores. So as you can see, the centralized scheduler has like a sweet spot in 8 cores, because then it's just 1 of 8 that's used for scheduling, so it's not too bad. And then if you go higher, you will reach the bottleneck of the centralized scheduler, so it will look like you have a lot of scheduling overhead, but it's just that the scheduler can't keep up. And for the distributed scheduler, the scheduling overhead is fairly constant. It goes up a bit with the core count. And from my point of view, this is really no numbers, maybe too low to be true. So there's some, I'm building a more real-world test application with real input and output to see how it behaves in a less synthetic situation. This is the status of the patch, or some pointers to further reading. There's a patch set that I sent out. There's actually 2 versions of an RFC, and then it's the first version of a proper patch set. There's documentation included in the patch set, of course, but actually the cover letter of the patch set has a lot more information, and also more information than I'm giving you today. So I recommend you reading that if you're interested. And I'm also recommending you to come with feedback and try it out. And my hope is that it's going to be included in 18.11 timeframe. That's all I had. Any questions?
A quick one. Is there any port to L-core correlation? Is every L-core supposed to have 1 port? Or
No.
use multiple ports?
You get the same level of freedom as you get with the centralized scheduler. So you can have 0 or more ports.
But if you have more ports per core, you have to pull them.
Correct.
Yes. And what's the expected, what kind of application overhead, the number of cycles spent in the application processing event? Do you think, is this intended for anything, or is this intended for low overhead applications or large overhead applications? Or both?
Well, it tries to address the shorter pipelines. Because if you have longer pipelines, then scheduling overhead doesn't really matter, and scheduler performance doesn't really matter because you don't have a lot of events.
It's the, okay, high event rate, but possibly because you have a long pipeline, so which multiplies number of packets by number of pipeline stages.
Yeah.
Okay.
Any other questions?
So we talked about the flow migration. So is that about load balancing the amount of load we have got on the port? As in, let's say a port has got 128 packets queued up, and then another port has got 2 packets queued up. So the flow migration is about moving the flow from the port with 128 packets to the port with 2 packets?
Yes, but we don't use the queue length as an input to the migrations.
Yes, I agree. You have
we look at the load on a longer time period.
Okay.
But yeah, we are moving, and that includes moving the flows, moving the events that are already queued to that port.
Okay. So does that mean that a CPU cannot read from multiple ports?
Yeah, our core thread can pull from multiple ports, yes, that's possible. And you can also have a situation where you migrate from one port that's owned by one L core to the same port that's owned by the same L core, or a different port owned by the same L core thread. So it's, yeah. But
okay.
That should, I mean, the higher, if you can have multiple event ports per core, and that would make sense, but what I would expect is the majority of the events, they arrive on one of those ports, so that they are really relevant for migration purposes.
Okay, thank you.
Yeah, so I have few questions, very simple questions. So for the reordering, how you eliminate the reorder for the reverse flow? So like the act before the data itself. So the forward and the reverse flows are not correlated here, right?
I'm not sure what you mean by reverse flow.
I mean the X. So the data is a forward and then the X on the reverse flow, right?
Yeah, but event them only don't care about the X. I mean, this ordering happens on a queue.
Okay.
So it's not.
So my second question is also, can you have a race on the least loaded L core?
If you can have a race.
Yes. Everybody is moving to this L core?
Yes, that's a good question. Yes, that can happen. That has happened. But what we do is you randomize when the ports are considering their migration. And then you have a load balancing, load estimate period that's shorter than the period in which between the migration. So we actually see, statistically, if you have like 12 cores and they're all busy, and then this idle core, then one core will move his flow, and then there will be some period of time before someone else is considering migration. So, but.
And my last question is, what's the logic that you are moving the smallest flow? Maybe a heavy hitter is coming, and then all the flows are moving to a new core. So what's the logic that you pick the smallest flow?
Yeah, the smallest of the last 120 unseen events. So it is active still. So it's, yeah. Well, the logic is, first of all, cache usage. We don't want to, if you have a really big flow that's on one core, you preferably you don't want to move that to a different core. And then also, if you move one of the big flows, it would create a lot of disturbance in the system, because probably that port that received this big flow would also be overloaded and have to move away his flow, and maybe he'll move the big flow as well. So, but that said, I mean, the migration strategy is something that needs to survive real-world applications as well, and then now it's just my speculation, basically.
It's working? No?
Yeah, is the throw mic working?
Hello? No? Not yet? Okay. So I know Ericsson has a long history with DPDK, and Jim presented the companies who are contributing, and I haven't seen your name, so I'm really happy to see that you guys are contributing. That's good.
Yeah, it's a lot of fun. I'm happy too.
I have two quick questions. The first one is this NUMA aware? Because if, for example, the packet's received on a device that happens to be associated with one particular socket, moving it over to another socket would make life really bad.
No, it's not new aware.
Okay.
Yeah.
And the other one is, have you looked into it all? There's kind of a Heisenberg effect, which is the way of measuring system clock rate using read TSC actually perturbs the CPU. And if you're really, really loaded on really high data rates, you can get things like when you start to add TSC counter probes to measure how many clock cycles you're taking, all of a sudden you slow down 10% because you're creating basically a CPU stall to read the TSC.
Yeah, well, we avoid as much as possible to read the TSC. It's just, just that can happen quite often, but at the point of transition between busy and idle. So
So you're measuring it when you think you're idle? Or
What's
you're measuring it when you're done with all packets, so you think you're idle?
we measure we measure when you go from busy to idle, and that happens, or the other way around, and that happens if you, as I mentioned, if you DQ 0, you're idle, and if you DQ more than 1, or more or equal than 1, you're busy. So then we take a timestamp.
All right.
So if you're very, very busy and you have events almost all the time, then you will very rarely do a timestamp.
Thank you.
Two questions. Have you measured it against a workload that's less cache friendly, I guess, that hogs the cache a bit more? And then the second question, you said that it's only atomic. You're not doing the ordered load balancing. Is that just future work, or is there some technical reason why either you don't think it's necessary or you don't think it's possible?
We did some preliminary integration into our product, and then that certainly used a lot of cache. But we didn't give any good performance indicators. So no, not really. I don't know to what extent application cache usage would impact scheduling overhead. And what was the second question?
Just around ordered, you mentioned that you...
Right.
I think you said it.
Yeah. Well, there's certainly ways to do ordered. Maybe more clever ways than the one I thought of, was basically just forward it one step further to a core that has a reorder buffer, and then you will shuffle things around. And that's certainly possible. And if you do it on the whiteboard, it looks simple. But if you do it in code, which I started to do, it will drive a lot of complexity. So, but yeah, that's something we should definitely look at, I think. But maybe not for the first release.
Okay, thank you.
Okay, thanks, Mattias.
Thanks.